Hey, welcome back to Stat 218, the last couple class recordings. Wow, it's been a weird and long ride. Do got to say though, I appreciate that you've stuck it out, and such things are good. So let me sort of open up what we've got going here for our class, and I believe it's PowerPoint. Damn it, where's PowerPoint? Okay, there we go. Just to put things in context of where we've been and where we're going, I did mention at the very beginning of the term, there's a lot of stuff early on about how to summarize data, and some of the material in chapter 10 and some of the material in chapter 12 really do relate to summarizing data. Correlation itself is a data summary, but we could wrap it into the context of a hypothesis test or a confidence interval. And same thing for a linear trend relationship, a regression line, if you will. Again, I view it as a data summary, but if a certain set of conditions hold, then you can even test hypotheses and do confidence intervals for relevant unknown population parameters. So when should you consider using a method like correlation or regression? Well, if you are looking at the chart, you can see that if the explanatory variable is itself quantitative, and the response is quantitative, you're saying, aha, we're in that situation where correlation and regression would be appropriate. And so if any of your variables are categorical or qualitative in nature, you're not going to be using linear regression at all. It's only dealing with quantitative and quantitative variables. Okay, so moving forward a little bit. If you're making a scatter plot, okay, we're going to recommend always putting your response variable on the y-axis and your explanatory variable on the x-axis. We are not economists. We're dating this back to high school where y'all in algebra thought of functions, and on the y-axis is where your range is, the domain is along the x-axis. X gets you a particular value of Y. And so if in a scatter plot, you want to look at the relationship between X and Y, the way you could do that is the following. Plot X along the X-axis, Y along the Y-axis. Okay, so let's grab data on one of these variables, and rather than maybe start with that one, those examples, broccoli or wine consumption, let's start with this corn yield and then the rainfall level. Okay, so I'm imagining here that if you think that the yield of corn in terms of bushels per acre depends on the rainfall level in one particular county in Illinois, right near the Mississippi River, you would think, okay, the response variable is yield, the explanatory variable is rainfall level. And if I were to create an analysis of that, I would think the yield may depend on the rainfall level. Click OK, and automatically in the wrong window, but that's always the case for me. In the wrong window, we see our graph appearing. Can you all see that there is a relationship that as the rainfall level goes up, the yield goes up? I'm seeing all of you nod right now virtually. Okay, so I'm thinking that the explanation is simple. If you don't have enough rain, you're not going to get much corn yield. If you have enough rain, you're going to get more corn yield. Overall, the trend is positive. Some would even say that, oh, look, it seems to be curved. I'm saying overall, I'd fit a straight line. And if you think a linear trend is relevant or perhaps important as a way of describing the XY relationship, you could go ahead and use that. Let's try another explanatory variable and response variable pair. I've got data here on the prices of homes, which is unfortunately labeled dot. I screwed something up in the process of downloading the data set, and I didn't fix it yet. So these are prices of homes that sold in the city of San Luis Obispo, okay, in 1998, and the size of the home in terms of hundreds of square feet, price in thousands of dollars. So for example, 232 is $232,000. 100 square feet, 19.95 means that's a 1,995 square foot home. And if I try to describe the XY relationship, I could do that again under analyze, fit Y by X. I'm thinking that the price may depend on the size of the house. I'm thinking you would expect so much and not much less. You don't find that larger homes tend to typically sell for more. They tend to, typically sell for less. They tend to sell for more. So we've got that relationship here. And you see in the scatter plot, the XY relationship very nicely shown. Okay. So the scatter plot basically shows the relationship. And we have a natural question of the following. Is the trend in our data, our sample data, so strong that we're convinced that there is an underlying trend in the greater population from which we've sampled? In other words, with the corn yield and rainfall data, would we see, if we sampled more years in this county, that again, the more data we have, we still see more rainfall begets more yield. And then similarly, if we see other homes, not just 1998 sales homes, but maybe 1999 as well, would I have larger homes selling for more? Okay, so the question is really, is there a trend that's strong enough that I'm convinced it's real? Our two methods are going to be correlation. We're going to do that one today. And then a confidence interval for a correlation, no, a hypothesis test about a correlation coefficient. And then the next two lectures will be dealing with regression. So here are some examples of correlations and scatter plots. You can see here, if I were to show you the correlation coefficient value R, you can see an R of 0 looks as though there's no relationship, okay? An R that's sort of, well, negative 0.95 looks like there's a very tight relationship. An R of positive 0.9, it's a little weaker of a relationship. An R of 0.7, weaker. An R of 0.4, even weaker. So as we have the value of R growing away from 0, the relationship becomes more clearly linear. Okay, secondarily, the sign here, R being negative in this case, and negative in this case, positive in the second and fourth situations, that corresponds to the direction or the slope of the correlation, okay, of the trend line, if you will. Okay, here is an equation for calculating the correlation coefficient. I have never asked in my life a student to calculate a correlation coefficient on a final. The conceptual formula is what I'm going to be emphasizing, but if you're alone by yourself on a desert island and all you have is your human blood and a volleyball to work with, maybe this equation that our textbook has in it would be a little bit quicker to utilize. It takes fewer steps with a calculator, if you will. The calculation formula, I'm going to blow it off entirely. Okay, I want to work with the conceptual formula and work that out in the context of maybe a scatter plot. So I'm going to try and draw a scatter plot here. Here's your X values. There are the Y values. Again, Y is the response variable. X is the explanatory variable. And I'm going to try and draw a couple dots to correspond to the data points in my trend. And maybe if I were to circle the trend line overall, not the trend line, the dots, if I put an ellipse around approximately 95% or so of the data points, that gives you an idea about the shape of the graph as well as where the bulk of the data are. First thing I want to do is to consider PEMDAS. PEMDAS says, let's look at just the parts inside the parenthesis first. So just this leftmost of the two parentheses, what I've got is How far above X bar is an individual data point? Okay, so how far above X bar is an individual data value expressed in standard deviations? Okay, so that's really the z-score for an X value. So relative to the average X, where do X values lie? Above the average X, we're going to have a positive contribution. Below the average X, that contribution would be negative. Okay. Secondarily, we see the same shape over here, except for relative to Y bar, above average gets us a positive, and below average will get you a negative. So in this first quadrant, you have above average in terms of X and above average in terms of Y. It's a positive times a positive, which results in a positive contribution to the overall correlation inside this equation here. Each data point will add a little bit of positivity if you're in the upper right quadrant. If you're in the second quadrant, upper left, you're below average in terms of X, while still above average in terms of Y. You've got a negative times then a positive, which results in a negative overall contribution to the correlation coefficient. So all the data points in this second quadrant, not so many of them, it looks like, are going to add a negative contribution. In this third quadrant, we have a negative times a negative, which is overall a negative contribution. So these are all negatively contributing. I'm sorry, negative times negative, which is positive. I apologize. Which mean if you're in the first or the third quadrant, you're going to add a positive number to this correlation. If you're in the second or the fourth quadrants, you're going to add a negative contribution overall. So you can see why conceptually a positive slope where the data will tend to be in the first and third quadrants would have an overall positive correlation. If on the other hand, you had the scatter plot looking somewhat differently, let's try a different looking scatter plot. If we find the data are stacked up that way, we would have a positive contribution here, negative, positive, and negative. The bulk of the data points are adding a negative into this calculation. So we would have a negative correlation if the data are stacked up in the second and fourth quadrants. We're typically going to use software to tackle the problem, okay? So let's maybe go ahead and look at an example of using software to tackle that problem. We've got another data set here, is data on some skyscrapers, the height of the building and the number of floors. You might ask yourself, which is X, which is Y? I tend to think it's easier to consider the height depending on the number of floors than the floors depending on the height. No one ever says, oh, I want a building that's 550 feet tall. How many floors can you jam into it? People say when they're building a skyscraper, oh, I need 54 floors. How tall should the building be? Oh, 650 feet tall. Good, got it. So stories or number of floors is X, height is Y. Okay, so again, I'm going to go ahead and do the scatter plot generation. The number of floors may predict the height of the building. Boom. Look at that. Okay. And here we go. Scatter plot. Do you see a positive correlation? I sure as heck do. Now, if I were trying to describe the nature of that relationship, I would do that with the correlation coefficient. So I'm going to go ahead and use a analysis method called find for me the correlation. Okay, it's not something that we're asking you to do with Minitab or JMP now, but if I were to take my two variables, height and number of floors, I could say find for me the correlation. It will show us a scatter plot matrix, if you will. Here's floors, depending the height in this upper right of the four graphs that are shown. The correlation between height and the number of floors is 0.9506. Fairly straightforward and easy to do. 0.9506 is my value for the correlation coefficient. Okay, so 0.9506. Let's go ahead and move forward. And when we do that, we're going to tell you some facts about the correlation coefficient. Some of them are pretty easy to see. Some of them are harder to prove to be the case. But R, as a measure of anything, just measures the strength of the linear relationship between X and Y. So I would say if your relationship is definitely not linear, don't use correlation. If someone walks up to you and says two variables are strongly correlated, they mean they're correlated in a linear fashion. A straight line would describe the general overall pattern. Second, correlations are always in the negative to positive one range. If someone calculates the correlation for you and says, oh, it's 1.9, no, they screwed something up. Correlations are always in the range negative to positive one. Correlations that are negative correspond to a negative relationship. Correlations that are positive will correspond to a positive relationship. Okay. The closer the absolute value of the correlation is to 1, the stronger the relationship. Going back a couple slides, you can see that. So going back a couple slides, you can see that as we go from a correlation of 0 to positive 0.4 to negative 0.7, well, the absolute value of that is 0.7, to 0.9 to 0.95, the relationship gets stronger and tighter and stronger. Okay, so the closer the correlation is to 1, the stronger the relationship. I would even go so far as to say, and I regret not putting it on the slide, but if the correlation is exactly 1, all the data points follow a perfectly straight line with all the data points collinear, if you will. Okay, so to use that geometry term from the past, a blast from the past, geometry, perfect correlation corresponds to all the data points are on a perfectly straight line. Okay, what about a correlation about 0? Well, that means one of two things is true. Either there is no linear relationship, okay, or there is a relationship, but it's not linear. Again, a correlation of 0 means there isn't a linear relationship. There could be a nonlinear relationship that has a correlation of 0. If I showed you the graph of y that's x squared, is there a relationship between x and y? You're thinking, heck yeah, there is. Because if I tell you x is 0, you know y is 0. If I tell you x is 1, y is 1. If I tell you x is 2, y is 4. If I tell you x is 3, y is 9. X being a negative 1 tells you y is 1. Negative 2 gets you a 4. Negative 3 gets you a 9. That is a perfectly straight, perfect relationship that's not straight. Okay, trying to capture all the data points here. A perfect parabola. Is there a relationship? Well, the way I ask you to consider that is the following. If I tell you X, could you predict Y? Perfectly. You would say, Y is what? If X is positive 4, you'd say 16. You can completely predict Y. There is a perfect relationship, but it's not linear. It looks as though in this case, we have a relationship where some of it is negatively correlated and some of the trend is positively correlated. Because it forms a mirror image, the overall correlation R is going to be 0. So a correlation of 0 doesn't tell us there's no relationship, just not that there's a linear relationship. Okay, moving on. If I want to test a hypothesis about a correlation, we can do that. The Greek letter rho, lowercase Greek letters are always in statistics an unknown parameter value. You could think the correlation between home size and then the size of the lot on the price of the home, okay? If rho were 0, that means across all of homes, there is no relationship between the size of the house and then the price of the house. A correlation of non-zero means there is a relationship. So, like always, we're going to believe no relationship until we're convinced that there is. Null hypothesis of no relationship matches across chapters 7, 8, 10, 11, 12. Every time we look for, is there a relationship or not, we're dealing with a null hypothesis of no relationship. Alternative, yes, there is. Our test statistic is t, and that's r times the root of n minus 2 over 1 minus r squared. Okay, so let's use our data from earlier and calculate that test statistic t. Okay, if I'm looking correctly, we've got our data here, and I've got the correlation, and I need to know the number of data points. So let me write down the correlation. R is 0.9506. And how many data points do I have? Well, that's hard to know off the top of your head. Oh, 60 data points. N is 60. So I'm going to implement my hypothesis test to see if this relationship is strong enough that I'm convinced that it's real. Your guess is probably, heck yeah, it's real, because it really looks quite noticeable. Okay, so my test statistic t should be 0.9506 times then the root of 60 minus 2 over then 1 minus 0.9506 squared. Okay, so that's a value I could calculate. I'm going to do that in green, and I'm going to pause the video to use my calculator and do that, and I'm going to encourage you to also pause your video so you can verify that you can get the calculation correct. Note, you do everything here, then take a root, and this being squared, subtracted from 1, I would probably start in the denominator, okay? So that's your hint. I'm going to pause the video while I do my calculation, and we'll see where we get to, and hopefully I get the right value. So hopefully you got the right value. The value that I got for my test statistic was 23.32. Okay, so if you get a value of 23, you are so far out in the tail of the t distribution with degrees of freedom, in this case, 58 degrees of freedom. Okay, I'm saying the p-value is small if we want to do a two-tailed test or non-directional test. Simply, is there a relationship between the heights of buildings and then the number of floors? You would say that p-value, which is these two tail areas taken together, the p-value less than 0.0001. If I did a quick calculation of it with my computer, 1 over. Just for emphasis. That is about 0. It's as close to 0 as you're going to get. I mean, I literally did the calculation, and to 18-digit precision, no, 16-digit precision, it's 0. So it's less than 0.00000, 18 zeros, 16 zeros in a row, 1. Okay, that's how small it is. So I would be convinced from the scatter plot and the correlation that it is statistically significant. And this procedure does rely on some assumptions which relate to not the sample size, but rather the nature of the data. We'll be emphasizing those later in chapter 12. Okay, want to mention one more thing, and that is the following. In your textbook, you might know that on one of the pages, there's this little section called optional confidence interval for rho. It's on page 519, and I'm going to say this will not count towards your final grade, but if I were to put a question on this, and I intend to put a question on this on the final exam, getting it right would get you bonus points. It's not going to get you tons of bonus points, but basically think an extra 10% of the test score. Like if the tests were worth 100 points, you could get an extra 10% from doing this question and getting it completely right. Okay, so I'd say that's something to look at, and I'm happy to chat with you in the discussion group over the weekend or in some other fashion to sort of help you go through the algebra here. It does take a little bit of time and effort, but the tool is simple. So if you want to take that on as an additional sort of thing to learn, you could boost your score by a little bit. And a little bit of 10% on one exam is actually not so bad. Okay, so that is a good place to stop for now. And then we're going to pick up at the next time with the introduction to linear regression.